Okay, in this section, 2.4, solving polynomials in factored or intercept form, we are going to actually start talking about solving our polynomials. So up until this point in this section, we've talked a lot about naming them, multiplying them, adding them. Now we are going to start using polynomials and different solving techniques to find solutions. So the first thing that I want to kind of rehash is what you guys have learned in the past. So up here at the top, I'm just going to draw a few notes. The first one I just want us to look at is the solving techniques that you're used to. So when we have like 2x plus 11, and that's equal to, say, 1, and you were asked to solve this equation, right? You said, okay, well, there's a variable x here, so I'm just going to try and get x by itself. I'm going to subtract 11 to both sides. Oops, that was weird. Both sides of the equation, right? We always have to do the same thing to one side as we do to the other, leaving 2x on the side by itself, and we're ending up with negative 10 on this right side. Now, then we divided by the 2 when you guys solved, and you would get x is equal to negative 5. This represented the solution, right? That was the value of x that if we were to have plugged in up here, 2 times 5, right? Negative 5 would give me negative 10 plus 11 would equal 1. On a graph, and we don't always make this connection, but if I wanted to graph this line and solve, I could actually put everything on one side. So I'm going to show you kind of a different technique we didn't use as much. But if we were to instead move this 1, so subtract it this way, and leave 0 on the other side, that would give us the 2x plus 10 when we subtracted that 1. Now, this essentially is just an equation, right? Like y equals, it's just backwards, mx plus b. I could actually draw a graph of this. I could draw a little function, xy. Notice here on my function, 2x plus 10, 10 is like my y-intercept. So if I came up here to 10, that's where I would start graphing my line. This is a very terrible graph, but if I then use the slope of 2, right, normally we'd go up 2 over 1, but that's going to go off my graph. So I'm going to go like down 2 over 1, down 2 over 1. And essentially when I draw this graph here, this piece right here where it's crossing this x-axis is actually going to be at negative 5. When you solve an equation or when you graph a function, your x-intercept is your solution. And that's one thing maybe we understood a little bit, but we're going to use a lot moving forward. Anytime I can't solve something algebraically, I can solve it graphically. Or if I know the solution, I can start to build my graph based off of that x-intercept. So you've done some of this solving in the past. This year we're going to have equations that look a little more like the one I'm going to write here. Maybe 2x squared plus 3x equals 0. Now in this case, again, I can move stuff to the other side of the equation, but I've got two terms with x, and they're not like terms, so I can't combine them. So we need new strategies to help us solve these equations, right? We've practiced the ones for linear equations. This year we're going to spend some time learning new strategies. The first one we're going to learn is factoring. Now again, we've been multiplying polynomials. We're going to go backwards and factor them to help us identify solutions. So let's first talk about this from a graph. The first question here says, where are solutions to functions on a graph? Well, I just mentioned the solutions are always the x-intercepts, okay? And when we say solutions, I'm going to talk about, these are real number solutions, okay? So we're talking about getting a real number solution. That will always be seen on the graph. Another word for solutions, because they're on the y-axis and they occur when they're on the x-axis, they occur when y is 0. Sometimes they're called zeros. So sometimes it'll say find the zeros of the function, and it just means find the solutions, or sometimes they're called roots. So just know that those terms are used interchangeably. So again, if we know that the solutions or the roots or the zeros are the x-intercepts, then we can look at these functions and we can try and use graphing to help us solve. I'm going to look at the one here on the right. This one, right, is a curved shape. So notice it's got two x-intercepts. If there are two x-intercepts, okay, I'm going to write this underneath. That means that there are two real number solutions. okay? And we solve them by identifying those solutions. So one of them looks like it's crossing at +6 and one is at 8. So it either needs to be crossing or touching, and it creates an x-intercept. So those both are solutions to the equation. Looking at this middle one, there's only one crossing part. This is linear, so it's not going to come back and cross again. So again, if there's one x-intercept, that means that there's one real solution to this function. And again, we can identify it from the graph. X would be equal to -2 in this case. Looking on the left, this one is a cubic function, so it has 3 x-intercepts, right? So 3 x-intercepts mean there are 3 real solutions. And it's pretty easy to tell where some of them are crossing. So like this one on the left looks like it's crossing maybe at -1. This one definitely is between 1 and 2. And then this guy right here is almost at 3. It's kind of hard to tell. If you can't tell where it's crossing on the graph, this one you need to solve algebraically. So if we can tell where it's crossing, then graphing is fair game. If we can't tell where it's crossing, then we have to take a step back, solve it algebraically to find those 3 real solutions. Okay. Let's connect the graph to the equation really quickly. So on this one, modeling with mathematics, it says you can model the arch of an entrance to a train tunnel using the equation given here. So we've got an equation right here, where x and y are measured in inches. So this is just a little guy. The x-axis represents the floor. So here's your floor, right? You guess you got a train, and here's the tunnel. And it says, describe how the width of the arch at ground level could be found using the graph. Now, if we're at ground level, we're on the floor, right? We're on that x-axis. We'll notice it's crossing here on the left, and it's crossing on the graph here on the right. So if I could find this distance between here, I would know the width of the tunnel. So on a graph, right, in this case, I just want to determine the distance between my x-intercepts. That would give me the width of the tunnel. Now, if you look at your graph closely, it's hard to tell where it's crossing. It's somewhere between our 15 mark and our 20 mark, but it's hard to tell, kind of like we talked about before. This is where the equation is going to come into play. So how can the equation help? So on B, I'm going to say use the equation to find the x-intercepts, because remember, the x-intercepts are just the solutions. So we could say use, or maybe we should even say solve, right? Because that would help us. So what I'm going to do is I'm going to show you how this works. So if we have, and I'm going to write this off to the right, y is equal to -1/9, x plus 18, and we've got x minus 18. Again, we want to find the zeros, or where y is 0. So if I let y equal 0 and I have -1/9, x plus 18, and x minus 18, essentially I want to figure out what values make this work. Now this is just an equation with 3 things being multiplied. So I have this piece right here, multiplied by this piece right here, multiplied by this piece right here. Now if you look at that, you've got 3 things multiplying to give you 0. So maybe it would make more sense just to look at really quick off to the side. If I have like 4 times 3 times something equal to 0, this value right here, right, it has to be 0. Because 4 times 3 times something is 0, and if you have anything that multiplies to 0, one of the pieces has to be 0. Nothing else works. If we put a 1 in, doesn't work. Put a 2 in, doesn't work. So essentially the cool thing about factored form, which we're going to use today, is that if this guy's factored, we can just look at the 3 pieces and say, well, what would make it be 0? So if you look at this first piece, -1/9, he'll never be 0, so he's not really helpful to our solutions. Then we look at the next piece. We have x plus 18. What value of x here, right, plus 18 would give me a 0 in this spot? Well, if we look at that, a -18, right, is what's going to create a 0. If you look at your x-intercepts, that works perfectly because this guy is between negative 15 and negative 20. That's crossing at negative 18. Using that same logic, this positive piece, we've got x minus 18, right? If I put a positive 18 in that one, that would give me this positive x-intercept over here. So once we know it's crossing at 18 and negative 18, then we can find the width of that arch. Now we're talking distance, so even though it's negative 18, let's use the absolute value bars because we want the distance, right, plus the other x-intercept. So if we add those, we end up getting 36 inches. Okay, now essentially the rest of this is pulling all of that together. That's kind of the application where we want to head, being able to use both to help us identify application problems. So in order to use this factored form that we like so much, we need to be able to factor the polynomial. So we're going to practice on some expressions and then apply it to an equation. So it says, first of all, what does it mean for a polynomial to have a greatest common factor? Well, that means that there's something that divides, right? The greatest value that divides out of every single term is our greatest common factor. Okay, so I know this doesn't make sense grammatically, but we're going to say a factor divides out of every term. And when it says greatest, you're going to use the biggest one. Okay, so looking down here, again, notice there's two terms on this first one. We're going to practice identifying greatest common factor. So we've got 2 and 10. Well, 2, the only factors of 2 are 1 and 2, right? But 2 works with 10, so if we know that 2 is going to divide into both of those terms, we're going to pull a 2 out. Now again, this is like backwards distributing, so when you divide something out, we're going to create those parentheses as if we were going to distribute, but we're dividing it out. Now, I like to write whatever my greatest common factor is over here underneath so that I remember to divide it out of every term. So the 2 divides out, leaving a y squared. 10 is then divided by 2, leaving a plus 5. Again, notice if we were to multiply this back in like we've been practicing, we'd get 2y squared plus 10. So we're just doing exactly the opposite. On the next one, we have 4x cubed minus 40x. Again, their common factor would be a 4, definitely. But notice they also have an x in common. So this guy has an x to give, and he has an x to give. And we can only do one x because that second term only has one x variable. Okay, so 4x is our greatest common factor. So again, we pull it out front by dividing it out of the terms. The first term, that 4, is going to cancel. Then we've got x to the third. Dividing out one of the x's leaves x squared. And negative 40 divided by 4 is negative 10. And then those x's right there are canceling. Okay. A couple more of those. So if we look at the next one, this one has 3 terms. And notice 5 divides out of everything. However, no x over here, so we're only going to use 5, right? 5 is the only thing that seems like it can divide into each term. So we pull a 5 out. Again, if you start with 3 terms, you should still have 3 terms at the end. They're just going to be factored. So we're going to have x squared on the first term. Negative 25x divided by 5 is negative 5x. And then 10 divided by 5 is a positive 2. And our last example, very similar to one of the other ones. A 4 divides out of both of those, and again, they each have a y to give. So we're going to divide 4y into both of those. So 4y, the 4's go away, right, on both of them. Y squared divided by y is just y. And then if you have 4y divided by 4y, anything divided by itself is a positive 1. So just make sure if you were to multiply that back in that we get the same answer. Okay, once we've done that, we should be able to go back and forth. Now, expressions, right, these don't have equal signs, and we're just using expressions, you'll notice, to help us practice techniques, okay? Once we practice that technique, then we put an equation related to it, and we actually start to use those expressions to help us solve equations. So we've practiced and practiced going from factored form into standard form, right? That's just multiplying. We get 2x squared, 2x times 5, we get 10x. That's perfect. Today, again, now we're going from standard form back to factored form. So when we look at the two terms, we say what's common? Well, they both can divide by 3m. So I pull that 3m out front so that it's in factored form. And when I divide that, I get 4m. And again, 3m divided by itself, right, is just 1. Once we put this into equation form, then we can start to solve. But again, we're doing the same thing. It's just an expression equal to 0. So it looks like we could divide a 2 out of both of those and an x. So if I divide 2x out, then I end up with 2x minus 3. Right? And then I want to make sure I bring that 0 with me. And again, we know how to go the other direction. So we could multiply this in and get 7n equals 0. So we just want to be comfortable going both directions so that we can solve. Once it's in factored form, that's the most challenging part. Then we just have to identify the solution. So again, this goes back to what I was talking about with the train tunnel. Fill in the blank with the appropriate value to make the mathematical equation true. If I have something multiplied by 8 and it equals 0, that something must be the value 0. If we're looking at the middle one, notice you have 9 times this piece. So I don't just want to put a 0 here because 0 minus 5 is negative 5, right? So in this case, we want to put a positive 5 in here because 5 minus 5 is 0. And then that would end up being true. So positive 5 would work there. The last example, we've got 4 times something times 1 equals 0. So again, one of the somethings has to be 0. So it's important on this, it says, is there only one possible value? The answer is yes, right? Because we need to have a 0. So one of the factors, that doesn't mean the solutions, but one of the factors must be equal to 0, right? If they're multiplying to 0, one of them has to be equal to 0. Oftentimes, if we have this factored and we have like x and x here, there's two solutions that are possible because either this piece can be made to be 0 and that solution would work out great, or we could make this second piece of our factored form 0, and that would also create a 0 that would work. So let me show you an example. If we look at this first piece, kind of like we did with the train tunnel, the only value plus 3 that would give me 0 for this piece is a negative 3. And if I put negative 3 in for x, right, in both of these pieces, notice that I get 0 here in the first piece and I get negative 8 in the second piece. Now it doesn't really matter what I get in the second piece because I got a 0, so that equation is true. So that's essentially what we're looking for. So in this case, one of our solutions is negative 3 that works. The other solution from this one would be a positive 5 because 5 minus 5 would be 0. That's called the zero product property. So if the product of two real numbers is 0, then at least one of them must be 0. So looking down here, we've got a product, or these two multiplied together. So again, I'm going to go through these rather quickly. I would maybe pause it and see if you can do these. Again, we say what value minus 4 would be 0? Well, it must be a positive 4 because 4 minus 4, right? That's the only value that works there. Again, then we look at the second piece. The value here that creates 0 would be a positive 9 because 9 minus 9 is 0, so our solution is 9. Don't get lazy. Make sure we're getting in the habit of writing x equals and x equals for our solutions. Continuing forward again, here we would have p, and it's a positive 5, so we need a negative 5 to add to get 0. And here we've got p minus 2, so a positive 2 would add to 0. Notice on this next one, it's squared. Doesn't really matter though, right? Remember, that just means there's two of these. And notice if I were to look at this piece or the other piece, they're going to have the same solution. So n is equal to 4. And you can have a repeated solution. I don't have to write it twice. You can if you want. Example 4, notice there's 3 x values here. So that means this one has 3 solutions. So either, and I'm going to look at this last one, either this could be a negative 3 to give us a 0 in that last factor. So negative 3 is one of them. Or this x value could be a negative 1. Or this x value out front, nothing's added or subtracted, so if he's 0 in and of himself, he's going to create a 0 there. Okay, moving the same, 5 is going to be the same. So x is 0, x is positive 7. If you end up in something that looks like this, where this would actually require a fraction value, and you're unsure of how to do it in your head, just take 4n minus 1 and set it equal to 0. and then solve that. So you know how to do that with linear. So we add 1, 4n equals 1, divide by 4, and we get 1/4. Okay, and then again, this one's pretty straightforward, and could be -3 there. Same idea here, you've got numbers in front, so just take that, 5x plus 3, and set it equal to 0, minus the 3 over, divide by 5, x equals -3/5. And the more you do that, the more you're going to realize that's the same pattern every time. I take this one, change its sign because it got added or subtracted to the other side, and then I divide this one. So x would be 1/2. Okay. Again, that's our hope, is once they're in factored form, they're pretty easy to pull those solutions out of. So we just want to make sure that we're practicing our factoring here on the last ones. So again, if the original equation is not factored, these are our steps. Step 1, move all the terms to one side. Now that's different than what you're used to, but remember we have lots of terms with variables. So once you do that, then you factor out the greatest common factor and then identify the solutions. So looking at example 8, this one's already equal to 0. Great, work is done. So we look for a greatest common factor. Notice they both can be divided by a. So we pull an a out front and we get a plus 5. We then find those solutions. So what would make this piece 0? Well, a could be 0 in and of itself, or a could be a -5. On the next one, notice it's not equal to 0, so we do need to take this whole term and move it to the other side. So I'm going to add 9x and add 9x, which gives me 3x squared plus 9x equals 0. That's our first step. Then we look for a greatest common factor. In this case, it looks like they both would divide by 3x. So we pull the 3x out front, and we end up with x plus 3. Then we identify the solution. So either x is 0 or x is -3. Now again, it's important that you guys are writing out each step. If we try and come over here and we say 4m is the common factor, and then we put 4m somewhere, we have this equal sign in here, it gets to be chaos very quickly. So we just take one of the pieces, right, subtract it over to the other side, and then we have 0 equals 4m squared minus 12m. Oh, I'm sorry, I wrote 12m squared. Oop. And then we can find that greatest common factor. So we've got 4m, 4m. We get 0 equals 4m. And we just simplify that. So the 4 goes away. We're going to have m, and it looks like -3. So again, two solutions here. Either m is 0, because it's out front, or the only value that would subtract 3 and give us 0 would be a +3. So again, make sure we're following those steps. Move all terms to one side, set it equal to 0, and then go ahead and factor it out. And write out that factored form. Make sure that we're comfortable understanding the notation there. If we don't understand how to write it, we probably don't understand exactly what's happening in relation to it. So make sure that we're comfortable with that there. Again, your goal there is to be able to factor so that we can solve. It's one of the strategies that we'll be using from here on out.